All right, so the first question is, what are the mechanics of directional derivatives and what do they mean? Okay, so mechanically, and how do you take a directional derivative? So for instance, if we just want to take a derivative of some function f with respect to x, then all we have to do is remember f here is a function of x, y, and z. So all we do is we just treat y and z as though they're constants, okay? And we differentiate as we normally would with respect to x. And the only subtlety here perhaps is that the partial derivative of, say, y and z, so y and z with respect to x, these are both 0, okay? So you just treat them like constants, and just like constants, if you derive one variable with respect to another, you'll just get 0, okay? Should we do an example, or is this clear to everyone? Okay, I guess I can just come up with one example. So if we have something like e to the xy, say zx, let's just take a derivative with respect to x, okay? So what we do is, remember, we have to apply the product rule and the chain rule, okay? So let's do the product rule first. So the product rule tells us that this is going to be d dx of e to the xy, so times zx. Oh, come on, don't stop writing now. This is not a good time for this. Let me check if is it low on juice. How do I figure that out? Oh, great. Man, I just charged it. Sorry, it's going to be like 30 seconds before it has enough juice. Do I have any questions while it charges for a second? Oh. Okay, can you break now? Yeah, okay, so I'll charge it again while you're working on your first problems. So, okay, first we take this derivative times zx plus, and then we leave the first part alone, and we take a derivative d dx with respect to zx, okay? So the second term is easier, and let's do that first. So we get e to the xy times, so the derivative d dx of zx, we just treat z as though it's a constant, and we get z. Okay, so for the first part, we are only differentiating this e to the xy. So we use chain rule. The outer function is just e to the something. The derivative of e to the something is just itself. And then we have to take the derivative of the inner function times zx. And this gives you zx times e to the xy times y, because again, we're just treating y as a constant. So plus e to the xy times z. Okay, so mechanically, that's how you take a directional derivative, or a partial derivative, I guess. Directional derivatives you'll learn later, where you generalize the idea of taking derivatives along the coordinate axes to taking a derivative along any direction. All right, so what does it mean? If we have some sort of curve, and we take, let's say that this is the x-axis. If we take a derivative with respect to the x-axis at this point, what we're doing is we're translating the x-axis so that it remains parallel to the actual x-axis until it goes through that point. Sorry, these are supposed to be parallel. Until it goes through that point. And then when you take a derivative with respect to x, you're just getting the change along this line. Okay, like the infinitesimal change of the function in that direction along that line. All right, great. And the same is true of y and z. So having said that, I also want to talk about taking limits. So I think I stated last week that there are some tricks that will allow you to determine whether limits exist in sort of a sure way. But I was actually mistaken here. There is no, or at least there's no way that I know that's simple and allows you to always determine quickly whether a limit in multiple dimensions exists. And the reason is because you just have infinitely many possible lines of approach towards some point. And it's very difficult to check them all. It's much easier to figure out when a limit does not exist, because then all you have to do is find two of these lines where the limit disagrees. But when you're trying to prove it exists, this is actually, in general, a very hard problem. And there are some ad hoc methods that work in special cases, but generally there's no algorithm that I know of to do this. And so let me tell you what the ad hoc methods are that either allow you to determine something exists or that it doesn't. So the main way to tell whether a function has a limit is to identify it as a polynomial or a rational function, okay? Because a polynomial, so you can assume that any polynomial, so f of x, y, and z, is a smooth function and all of its limits exist, okay? So if you can somehow bound the denominator above 0 and identify a polynomial in the numerator of some rational function like this, so if you can get a bound on this and you can identify that as a polynomial, that is the best way to determine whether a limit exists, okay? The other good method for determining when limits don't exist is to use polar coordinates, okay? So polar coordinates. Polar coordinates are not 100%, but the reason they're a good method is because they allow you to quickly check all linear approaches to the origin, okay? So any straight line that you can follow to the origin, you can check that quickly with polar coordinates. Now, if there's some crazy curve that approaches the function, that approaches the point where you're taking the limit, and that function is nonlinear, then the polar coordinate method will not work because it won't catch that strange curve that's nonlinear. But the way that you check all of the linear curves is basically, if you have a function of, we'll just start with x and y, g of x and y, then what you do is you plug in r cosine theta for x and y, so f, and g r cosine theta, r sine theta, and then you take a limit as r goes to 0, because taking a limit as r goes to 0 is the same as going to the origin. Or if you're not trying to go to the origin and you're trying to go to some other point, say that you're trying to go to like 4, 5 or something. You want to limit as you want to limit as x, y goes to 4, 5. Then what you can do is exactly the same thing, you just translate. So then you want x to be 4, so you just do 4 plus this, 5 plus this, 4 plus this, and 5 plus the r sine theta, okay? And then what you end up doing is you get the lines going inwards towards the 0.45. And so if you take this limit and the result is in terms of r only, meaning that theta doesn't change the limit depending on which theta you choose. And remember, thetas correspond to the direction of approach here. So if you take a limit and it doesn't depend, okay, well, fair enough. Maybe you'll only use polar coordinates to go to the origin. But let me tell you that it's pretty easy to extend them to other points, right? You just translate the function up, okay? Right, so when you're done, if the function only depends on r, then you can be sure that at least along all of the linear paths, the limit is the same. But if there's some theta term that's left in the expression that actually changes the answer, then you know that one of the linear paths breaks the idea that there is a limit that's well defined at this point or this point, okay? All right, so having said all of that, let's work out the worksheet. So give me F's in the chat when you have the worksheet up. Okay, good. Right, so let's start with problem one. Problem one is a bit of a warm up. 1A. And give me either F's or C's in the chat when you're done. Problem 1A, the first one. Oh, I'll write it on the screen. I don't know if the solutions to the week 5 and 6 worksheets will be posted.